Alrighty, in this video we are going to be talking about u-substitution. U-sub, right. So for number 1, we're going to let f of x is equal to 2x plus 1 cubed. And we want to verify that f prime of x is that lovely thing right there. So we're going to use the chain rule. So f prime of x is going to be 3 times 2x plus 1 square, and then using chain times 2, 6, 2x plus 1 square. Number 2 says we want to figure out why the integral of 6 times 2x plus 1 squared dx is equal to 2x plus 1 cubed using the opposite of the chain rule, which is going to be, plot twist, u-substitution. We're going to observe some of the other patterns below, so these right here. So pause the video, think about why this works, and then we'll talk about why. All right, so here's the problem with number 2. I can't really integrate this right here because I don't have any methods on integrating 2x plus 1 because this is basically a composition. However, I could probably integrate something like this where we substitute 2x plus 1 as u. Now, if I do that, where I substitute in u being 2x plus 1, then I'm going to have to make sure that my dx isn't going to be dx, but it's going to be du. So I'm going to have du is equal to the derivative of 2x plus 1, which is just 2 dx. And then I'm going to divide by 2. So I have 1/2 du is equal to dx. The reason why I have that is because I want to make sure that everything's in terms of u. So if I substitute everything in, I'm going to have the integral of 6 u squared. And then we know that dx right here is going to be substituted as 1/2 du. Which then gives us 3u squared du. Which then I could integrate 3u squared to be u cubed plus c. And then knowing that u is 2x plus 1, I'm going to substitute u to get that right there. So 2x plus 1 cubed plus c. Obviously, if you didn't want to use substitution for number 2, you could multiply this out. However, something like these examples right here, you probably don't want to multiply them out. All right, so let's look at number 3. To figure out what your u is, remember that it has to look like a composition. So I can't have u being 15x squared because that's not a composition of functions. Instead, looking at this one right here, where we have x cubed plus 2 to the 4th power, I'm going to have x cubed plus 2 represent u. I'm going to have du is going to be 3x squared dx. So that dx is 1 3x squared du. So whenever I do my substitution here, I'm going to have 15x squared. I'm going to have u to the 4th. And then my dx is going to be 1 over 3x squared du. Simplify this a little bit. We are going to get 5 u to the 4th du. Integrate using power rules. You're going to get u to the 5th plus c. And remember that u is x cubed plus 2, so I'm going to substitute that back in to get to my answer of x cubed plus 2 to the 5th plus c. Because my original function or my original integral was in terms of x, I want to make sure that my final answer is also in terms of x. Now, looking at these two problems, you might notice that whenever I am trying to figure out dx, it's basically going to be the reciprocal of whatever my derivative is right here. So here, 2, the reciprocal of 2 is 1/2. The reciprocal of 3x squared is 1 over 3x squared. So as a shorthand for these next couple of problems, I'm not going to solve for dx, because in order to solve for dx, that's just you taking the reciprocal of whatever we have. So looking at number 5, I'm going to set u to be 4x squared plus 1 because that is my composition, which means that du is going to be 8x dx. And if I were to solve for dx, it's going to be the reciprocal of 8x. So instead of doing everything, I'm just going to have 8x over 8x square root of u du. 8x over 8x is just going to be 1, so I have the integral of u du. And then remember, that's just going to be u to the 1/2 du. Integrate using power rule, so you're going to have 2/3 u to the 3/2. That's one of the basic functions I should memorize by now, hopefully. So then we have 2/3 u to the 3/2 plus c. I'm going to have 2/3 4x squared plus 1 to the 3/2 plus c. All right. So, number 6. I'm going to set u to be my composition, aka whatever my composition is. So in this case, x to the 3rd plus 3x. I'm going to find du. So du is going to be 3x squared plus 3 dx, which means I'm going to have the integral of x squared plus 1 over 3x squared plus 3 u to the 4th du. I'm going to simplify this a little bit. I could take it a 3. So if I take it a 3, I'm going to get x squared plus 1 over 3x squared plus 1 u to the 4th du. I'm going to cancel out the x squared plus 1, so that means that I'm left with 1/3, and I'm going to take that out. So I have 1/3 times the integral of u to the 4th du. Integrate that using power, so I'm going to have 1/3, 1/5, u to the 5th plus c. That's going to give us 1/15, and then x cubed plus 3x to the 5th power plus c as my final answer. Now, for something like number 7 here, once again, we want to figure out what my composition is. Since I have a square right here, u is probably going to be sine. Now, let's say that you didn't know that u was going to be sine, and let's say that u was cosine. If you treated u as cosine, then du would be negative sine, which means I'm going to have the integral of sine square x over negative sine of x u du, which means I have the integral of negative sine x u du. Because I have two variables, so x and u, that's why I can't really choose cosine to be u, because I have an x right here and I have a u right here. I have two variables, and I don't want that. So that's why here we want sine to be u, and then cosine to be du. So that whenever we do integrate this, I'm going to have u squared cosine x over cosine x du. Cosine x will just cancel out, so I'm just going to have u squared du. Take the integral of that, so the antiderivative of u squared is just 1/3 u to the 3rd power plus c. U is sine, so my answer here is 1/3 sine cubed x plus c. All right, so something like number 9 here, where we have the integral of tangent x. We don't know anything about tangent. However, we do know that I can rewrite tangent to be sine of x over cosine of x dx. Once again, you probably want to figure out what your u and du is. So here, if I let u to be sine of x and du be cosine of x, then I have u and then over cosine of x times cosine of x du, which means that I have u over cosine square of x. And I don't want that. So we need u to be cosine and du to be negative sine of x dx. So that once we do that, I'm going to have the integral of sine of x over negative sine of x, and then cosine of x being u. Sines will cancel out eventually, so that means I have the negative integral of 1 over u du. And remember that the integral of 1 over u is ln of the absolute value of u. Make sure that you have the absolute value, or else it's going to be incorrect. So you have negative ln of absolute value of u plus c. We know that u is cosine, so we have negative ln of cosine of x plus c. Okay, so those were your indefinite integrals where we had plus c. Using definite integrals where we have bounds of integration right here, like number 10a, we're going to evaluate this using the bounds of integrations in terms of u. So what does this mean? This means that we're going to change these bounds in terms of u, because right now it's an x. So we're going to use u-substitution. So using u-substitution, I'm going to have u being x cubed plus 3x, and du being 3x squared plus 3. Which, honestly, I could factor out to be 3x squared plus 1. Okay, so then if I take the integral here and I use all my substitution, the x squared plus 1 and the x squared plus 1 will cancel out here, which means that I'm just only left with 1/3, because remember, I'm going to take the reciprocal of whatever this is right here. So I have 1/3. And then I have u to the 4th du. Now, my bounds are not going to be from 0 to 1 because notice how here my variable is in terms of u. Because my variable is in terms of u, I'm going to change my limits so that it matches up with u right here. My lower limit is 0, so I'm going to plug in 0 in terms of my u here. So u of 0 is going to be 0 cubed plus 3 times 0, or plot twist, 0. Using 1, I'm going to have 1 cubed plus 3 times 1. 1 plus 3 is 4, which means that my upper limit is going to be 4. Okay, so if I were to take the integral here, I'm going to have 1/3, 1/5, u to the 5th from 0 to 4. And then I'm going to simplify this to get 1 over 15, u to the 5th from 0 to 4, 1/15, 4 to the 5th, minus 0 to the 5th, which is basically going to be 0. So then you have 1/15 times 4 to the 5th. What is that? I don't know. It's, I don't know, probably a big number, but you could just leave it like that and call it a day. So 99% of the time, we are going to be using this where we are just going to leave it in terms of u. So we're going to change my bounds of integration with u. Now, number 10b is going to be the same thing as 10a. We're going to get the same answer. However, we're still going to use my bounds of integration in terms of x. So what does this mean? Well, we're still going to have u being x cubed plus 3x. and du being 3x squared plus 3, or 3x squared plus 1, which then you are going to get 1/3, and then the integral of u to the 4th. Now, because you have u to the 4th, I can actually now substitute in u with x cubed plus 3x. So this is going to be x cubed plus 3x dx. And then my bounds are still going to be from 0 to 1 because my variable is in terms of x. And of course, well, let me do this again. So you're going to do the same thing here, actually. So I'm just going to copy and paste this right here. The only thing that's different is going to be your last steps. So here, my bounds of integration was from 0 to 1 because, not 0 to 1, 0 to 4 because we changed the bounds in terms of u. But if I were to substitute in u for x cubed plus 3x, my bounds are not going to be from 0 to 4, but it's going to go back from 0 to 1. And then we're just going to evaluate that. So I'm going to have 1/15. 1 cubed is 1, plus 3 times 1 is 4. And then this is going to be 0 whenever we do 0 here. And that should be to the 5th, isn't it? So we're going to get 4 to the 5th over 15. I know that was messy, but essentially for 10b, you're going to do the same steps here, except instead of u, you're going to substitute it back in to get x cubed plus 3x here, and then change your bounds back to 0 and 1. Because this is an extra step, you should probably just do 10a and call it a day, where you just change the bounds in terms of u and then evaluate it there. Okay. So let's do number 14, where we have a definite integral. I'm going to have u be 1 minus x squared and du being negative 2x. dx, of course. I'm going to change my bounds now. So instead of 0 to 1, I'm going to have 1 minus x squared. So 1 minus 0 squared, or just 1. And then if I go from 1 here, my upper limit of 1, that's going to be 1 minus 1 squared, or 0. Using my substitution now, I'm going to have x over negative 2x, the square root of u du. Notice how the x's cancel out, so I'm only left with a negative 1/2, which I will put it up front. All right, so once we do that, I am going to take the integral here. And remember that the antiderivative of the square root of u is going to be 2/3 u to the 3/2. I can take out the 2/3 so that I have u to the 3/2 from 1 to 0. So now I have, let's see, negative 1/3, and then 0 to the 3/2 minus 1 to the 3/2. 0 to the 3/2, 0, and then 1 to the 3/2 is minus 1, so that's going to give you negative 1. So that's going to give you an answer of 1/3. Okay. Same thing for 15. I'm going to look at what my u is going to be. Whenever you have a fraction like this, most likely your u is going to be your denominator. Notice how here I have 1 plus 5x squared. So my du needs to be 1 power less than that, which is going to be 10x. And since I have x right here, it's going to eventually cancel out. Dx, of course. All right, so from this, we're going to have the integral of 1 plus 5 times 0 squared. So that's going to be 1. And then if I were to substitute n1 here, I'm going to get 1 plus 5 times 1 squared, which is going to be 6. So my bounds are going to be 1 to 6. I'm going to have x over 10x u du. Notice how the x's will cancel out, so that's a good thing. I'm left with 1/10, which I could take up front. And that u should actually be 1 over u. So now I have 1/10 times the integral of 1 to 6 of 1 over u du. And remember that this is going to be, the integral of 1 over u is going to be ln of u, the absolute value of u, from 1 to 6. And since 1 through 6 is positive, I can actually remove the absolute value so that I get 1/10. And then we have ln of 6 minus ln of 1. Now remember that ln of 1 is just going to be 0, so technically I'm going to have 1/10 times ln of 6 as my answer.
There has to be a better way to get the ice off the car. I mean, I'm using the discount
Okay.
card, so I'm only getting 50% off.
16, last one that I'm going to do. I have the integral of 0 to pi over 4 of secant square of x times the square root of tangent x dx. Because you have a square root, probably leave that as my u. And your du is going to be secant square of x dx, which is perfect because then this will cancel out, which I'm not going to do. So now you're going to have the square root of u du, but we just need to change my bounds of integration. So if u is tangent of x, we want to figure out what tangent of 0 is, which is 0. And then I want to figure out what tangent of pi over 4 is, which is 1. So now I have the integral of 0 to 1, square root of u du, the integral of the square root of u, and hopefully by now you should know this, is 2/3 u to the 3/2 from 0 to 1. I can take the 2/3 so that I am only focusing on u to the 3/2 from 0 to 1. So then I get 2/3, 1 to the 3/2 minus 0 to the 3/2. 1 to the 3/2 is just 1, and then 0 to the 3/2 is just 0. So I'm just left with 2/3 as my answer. All right. There are some problems that we haven't done, like 13, 12, 11, 8, these 4. So do those for practice, and then whenever we get into class, we'll do more in terms of these types of problems and changing my bounds to be in terms of u instead of x.